Hello, everyone. Okay, so accumulation, we're still practicing. We had an FRQ on a total function, and we did accumulation type things. But now we're going to get into a new topic called differential equations. And we're going to learn one of the first things we do with it, which is called linear approximation. So, sounds like a lot. It's really not so bad. First, let's quick review, just to keep track of kind of the major themes we've been seeing this semester. So in the FRQs you've seen, you see this a lot. They give you the derivative, so f prime of x. You basically just have to find info about original function, whatever that may be. That's kind of the big theme of second semester calculus. You're always given you're always given the derivative and or the rate, and you're asked questions about the original function. Given a rate, find things about a total. How have we seen the rate given? Sometimes we see it given as an equation. Sometimes we've seen it given as a table. Sometimes we've seen it given as a graph. Sometimes they give you this whole notation. Well, what is this saying? Same thing. They're giving you the derivative graph and asking questions about the original. So this is that whole thing where g prime of x equals f of x. So the graph is the derivative. So it's a lot of different ways of me giving you the derivative and you telling me things about the original. Others is like given the rate, like r of t dt, or not r of t dt, just r of t. To give you a rate function, same thing. They're giving you a derivative and asking questions about the original. So all of the things we've done so far and will continue to do involve you giving given a rate, and you got to answer questions about the total for the most part. Sometimes, like today, they gave you a total and asked you to do things about the derivative and the rates. It's all about keeping these things straight, though. Am I given a rate? Am I finding a rate? Am I finding a rate of a rate? That's the stuff we have to keep track of. So today, the difference is going to look only a little different at first, but it'll be a little bit different as we continue to go on. They're going to give you the derivative, so nothing different there, but they're going to give it to you using this notation today. But it still means derivative. We're just going to start to see this notation for a reason I'll get into later. So we're going to start to use the dy dx notation when we're dealing with something called differential equations. Okay, so before we get into the weirdness of what's different about this, let's do a quick example. So given the derivative, dy over dx, equals 2x plus 1, and they'll give you an initial condition like f of 1 equals 3. Approximate f of 2 using a. And here it is, linear approximation. Now, that sounds intense, but really, it's something we've done before. Linear means a straight line. Approximation means you're not going to find the exact value. So a linear approximation just means a tangent line. Use a tangent line. We've done this before, so this is good, because if you're like, what's a tangent line again? Great, we need to go back and review it. So you're making a tangent line at this coordinate. So here's your point. So your point is 1, 3, and here's your slope. And we're going to make an approximation here using we're going to make a tangent line and then approximate. So let me show you how this works. First, we have our point, which is 1, 3. Now we need our slope. How do you get the slope? Remember, we want a specific slope, not the general formula for the derivative. So we plug the point into the slope. We plug 1 in because there's no y spot. 2 times 1 is 2, plus 1 is 3. and we make our tangent line y minus the y coordinate equals the slope times x minus the x coordinate. So we've done this, and in the past when I said make a tangent line, I said to just keep it like this. Here's what we're going to do now, just to add to this. We're going to isolate y. So the easiest way, you don't even have to distribute, just move the y term to the other side. So I added it over. And now this is what's happening. We basically have a function that we don't know what it looks like. We have the slope at each point. We know the slope is this equation 2x plus 1. I gave you this starting point of 1, 3. So in the original function, I know 1, 3 is a point. We're going to make a tangent line at this point, which we did. And then we're going to see if we can figure out what's happening at f of 2. To do that, plug 2 into your tangent line. And let's see if we can figure out what's going on. So we are basically approximating f of 2 by plugging 2 into this linear approximation. And when we do the math, we get 2 minus 1 is 1 times 3 is 3 plus 3 is 6. So f of 2 is approximately 6. Okay, there's more to this, so stick with me. But here's what happened. Basically what happened was we have an original function that we can't tell. I mean, you could in this case because you could integrate this sort of. We'll get to that in another day. But yes, you could integrate this, it's x squared. It's some kind of parabola. And I gave you the initial condition 1, 3, which is like right here. The parabola does something along these lines, I think. Essentially what we did was we created a tangent line right here to this point, and then we plugged in 2 to the tangent line. And we got this approximation of 2, 6. This was our original, 1, 3. Using a linear approximation. So was our answer the exact value of 2 in the original? No, the real value is somewhere up here probably. So as a follow-up, I'm going to ask you this question. Is our approximation over or under the actual value? Over or under? And if you look at our picture, because of the fact that the graph increases at an increasing rate or is concave up, we could see that our linear approximation was under the real value. How do you prove this without having to use words? Just find the second derivative. So go to your dy dx derivative equation and find the second derivative using implicit differentiation, or in this case, just find the second derivative. This was the notation, and just take the derivative like normal. Derivative of 2x is 2, derivative of 1 is 0. 2, there's no x values, that means the entire graph is concave up. Which means if the graph is concave up, like in this picture, and we did a linear approximation, it bends up, but our linear line is a straight line, so we under-approximated the actual value. And that is what is going on in this particular problem. We also could have plugged in the x coordinate, 1. There was nowhere to plug it in this case. That'll be a little different in the next problem. And then we could have seen if it was concave up or down at that point, and then we could tell whether or not our linear approximation is over or under. All right, so that's the idea of what we are doing today. I give you a derivative and an initial condition. You make a tangent line. You approximate the value using a tangent line, and then you tell me if the approximation is over or under. So really, we've done all this before. So why is this different today, or what's different about differential equations? Here's what's different about differential equations. Ready? Given dy over dx equals 2y plus 1 with f of 0 equals 3. Approximate f of 1 using a linear approximation. What's the big difference here? That's something we have not seen before. The derivative has a y in it. So we're going to have a mix of x's and y's now in our rate function. Why is that so beneficial? Or why is that a thing? Because now you can create really interesting rate functions that look entirely different from what we've seen because they're based on the output at that point. So the discussion, I asked you about this really important, interesting differential equation. And this one's actually going to be similar to the one we're about to do. But why is this one so significant? This is saying the slope equals the y-coordinate at every spot. So like if the y-coordinate was 1, the slope would be 1. If the y-coordinate was 2, the slope would be 2. If the y-coordinate was 3, the slope would be 3. If the y-coordinate, like, it's getting steeper as it goes, based solely on the y-coordinate, not the x-coordinate in this time. So that's going to be a thing that is pretty interesting. We're going to start to see really interesting differential equations and different ways we can change the rate by expressing the derivative with y in it instead of x, or a combination of both. But everything is the same. So we still do everything the same way. So let's get our point. Well, I gave you the point. Most of the time I will. But what about the slope in this case? The slope in this case, we plug the coordinate in. But just like we saw with implicit differentiation, this time we're not plugging x in. There's no x to plug in. We plug in y. So 2 times 3 is 6 plus 1 is 7. And now we make our tangent line, y minus the y-coordinate, equals the slope times x minus the x-coordinate. And that gives us this tangent line. So now, to approximate f of 1, we're going to use the tangent line. 7 times, this is still an x though in the tangent line. So now the x gets plugged in, plus 3, and f of 1 is approximately 3, which was kind of a stupid approximation because it just happened to be the same coordinate, but that's fine, because then we could continue on and we could approximate f of 2 and so on. But the follow-up, is this an over approximation or under? Well, it's the same value. Let's change this ever so slightly. Let's do this. Sorry, I want to do something. Let's change this to f of, change our initial condition. F of, oh wait, no, never mind. What am I doing? We're fine. F of 1. F of 1. There we go. Okay, I need something that was off. 7 times 1 plus 3 is 10. Okay, better. So here's what we just did. So in the original function, I know 0, 3 was a coordinate. So the graph does whatever it does, and I just approximated 110, which is way up here. So now I can tell, is this an over approximation or under, by using the second derivative. So the second derivative is equal to, take the derivative of the differential equation. Derivative of 2y is 2, but don't forget dy dx. We took the derivative of a y term. Can't forget that stuff again. And then we plug the derivative equation back into this. So this is all that implicit differentiation stuff we haven't seen for a while. We did spend a lot of time here though. And then we get this. And I'm asking about the concavity of the graph at this point. At the point where y is 3 in our initial, so when y equals 3, we plug in 3, and we get the second derivative is, so the second derivative in this case is 14, which means the graph is concave up here. The second derivative is a positive value, which means the graph was concave way up. And we approximated right here using just a linear approximation. So again, this is an under approximation because we were concave up. If we had found that the graph was concave down, our linear approximation would have been over. But in this case, it was an under approximation because we were concave up. All right, let's try another even more interesting one. What if I give you one like this? Xy with f of 1 equals 2. And I want you to approximate 2. Keeping it pretty simple today. Oops, sorry. There we go. All right, same logic. We got our slope, we got our point, so our point is 1, 2. Our slope is to plug the point into the slope. And look, in this case, we have both variables, x and y. So plug in both x, which is 1, and y, which is 2. That's our slope. So when we make our tangent line, y minus the y coordinate equals the slope times x minus the x coordinate. And we get y minus 2. Nope, I'm going to add it over actually. Y equals 2 times x minus 1 plus 2. And now I want to approximate f of 1, or f of 2. F of 2 is approximately 2 times 2 minus 1 plus 2. Which is 2 minus 1 is 1 times 2 is 2 plus 2 is 4. So f of 2 is approximately 4. All right, but then I want to know over or under approximation, and you have to explain yourself. That's what the second derivative will allow us to do. So check this out. This is a nice little time to review and remember that, we need to take the second derivative using, do not forget the very important things like product rule. We have one function, we have another function. So derivative of the first, derivative of x is 1 times the original second, plus derivative of the second, which is 1, but you took the derivative of a y term, times the original first. And then you can't have dy dx in your answer, so this gets plugged in. So our second derivative is y plus xy times x. That's the second derivative. In other words, y plus x squared y. And I want to check the concavity at our initial condition. So plug our coordinate into the second derivative. A lot of times you'll see this notation. Second derivative at the coordinate 1, 2 is, and plug it in. Y is your 2 plus x is your 1. 2 times 2 is 4. So at our point, we are concave up. We've been concave up for most of these. A lot of the ones we're dealing with right now are all increasing differential equations. So concave up, which means we're in under approximation again. So if it's a positive second derivative, it's concave up, if the original is also increasing. So if we have a positive slope and we're concave up, it is an under approximation. So under approximation. Okay. So it turns out every single problem we've done so far, we're going to learn a method for finding the original function. So in this first one I gave you, we could just integrate and find that the original function is x squared plus x, and we could solve for c. In this one, there's actually a way to integrate this and solve for it, and we would find something interesting. And the one we just did, there's a way to integrate this. It's kind of like reverse implicit differentiation and get the original function. So oftentimes, we're going to do something where we find the original function anyway, so we don't have to approximate. But every so often, there's going to be differential equations that you can't find the original function. So last example, dy over dx equals x plus y. This is called, and we'll learn more about these later, this is called a non-separable differential equation. You cannot find the original function of this using any convention in this class. There are other ways that you would learn about in a class called differential equations, where you start to learn how to find what's called particular solutions. Not here. Here we are just approximating and doing some other things that we'll learn about next time. But if I give you an initial condition, f of 3 equals, let's say, -2 in this case, approximate f of 4. Again, we're using linear approximations. There's actually a better approximation strategy called Euler's method that in BC we do, but not here. All we have to do is linear approximations. So again, we're using a linear approximation. All right, so again, we have our point, 3, -2. We have our slope, which means plug the coordinate into the differential equation and add in this case. So 3 minus 2 is 1. So it's kind of a cool way to talk about a derivative. We haven't seen it as a combination of like x plus y. That's pretty interesting. that creates a really interesting rate function that allows you to do some pretty interesting things, model like actual ways things are changing with more accuracy. So like our Hamilton beard problem and some of these other mosquito problems are all more or less realistic, not really. But as you add to this, you'll find out that the things you learn in Calc AB are the foundation. And then when you start doing Calc BC and you go into multivariable calculus and differential equations and analysis, you just build on it. It's really all of the calculus is always going to be there. But for those of you guys going off to be engineers or other people that model rates and whatnot, it's all the same stuff. Statisticians, all of them use calculus and then just build on it. All right, so we create our tangent line, y minus the y coordinate equals the slope times x minus the x coordinate. Here is my tangent line. And now we can approximate f of 4 is approximately 4 minus 3 minus 2, 1 minus 2, which is approximately -1, so it's still increasing. And then is it an over or under? Let's take the second derivative, so d squared y over dx squared is, derivative of x is 1, don't forget the 1. Derivative of y is also 1, but you took the derivative of a y term, so dy dx. And then we can't have dy dx, so plug dy dx in, for what it is, 1 plus x plus y. And that gives us 1 plus x, our original x, which is 3, plus original y, which was -2. And we get 3 minus 2 is 1, 1 plus 1 is 2, positive, so concave up, which means the graph goes like this. Our linear approximation was under. So we only saw under approximations. I guess I'm not super creative today. We'll see over approximations down the road when we start doing more interesting problems. But that's it. So again, I'm giving you a derivative, asking questions about the original. The only difference now is a little bit difference in the terminology and the way I'm expressing the derivative. The derivative is not going to be just x anymore. The derivative is going to be a combination of x and y. The dependent variable y is going to be a part of the derivative, and that's called a differential equation. All right, that's it.